Welcome everyone, and thank you for listening. Today I will be talking about approximating the requirement cut problem with a configuration LP. My name is Yotam, and this paper was made with my supervisor, Roy Schwartz. So in this problem, we have a graph with the edge weights and G sets of vertices that each have a requirement that is between 2 and the size of the set. And what we want to achieve here is finding a set of edges that when they are removed from G, they break each set of vertices who at least are connected components. Now let's look at an example. Here we have a group X with the green vertices, and it has a requirement of 3. So we want to separate the green group here in the graph to 3 different connected components. So for example, it will look like this. So for example, here we can disconnect the edges from E and D, and then we have 3 different connected components, E, D, and G with F. So this is a valid solution. What we want to achieve is a solution like this with the minimum cost on the edges we disconnected here. So after we have a solution from the configuration LP, we want to round it, and we use a similar method to the randomized rounding in the set cover problem, except for a few differences. So what we do is we take the lambdas of the cuts, and if the lambda is big enough, then we will pick it anyway. In this case, we chose it to be bigger than 2/3, and if not, then we choose it with a probability of lambda. And so we repeat this process until all the requirements are satisfied. So the main difference between this method and the rounding in set cover is that after an iteration, what we do is we resolve the configuration LP because this approach is a bit more complicated here than the one in set cover, and this makes the solution and the proof also a bit more complicated. So the main reason this problem is interesting to research is that it generalizes a lot of different classic cut problems. For example, we have here the multi-cut problem, in which we receive a graph and k pairs, and our goal here is to separate those pairs by removing edges from the graph with the minimum cost to these edges we want to remove. So for example, we see that in the image to the right, if we remove the yellow edges, then we will achieve our goal. And if we want to see that how this is a specialization of the requirement cut problem, then we can put 2 as the size of each group, and for each requirement we also put the size of 2. And we see that it comes to be the same problem. Another problem that is a special case of the requirement cut problem is the multi-way cut. In this problem, we receive a graph that has k special vertices called terminals. As we can see in the image to the left, the regular vertices are blue and the terminals are light blue. And so our goal is to separate all the terminals in the graph from one another And if we look at the image to the right, we can see that if we remove the red edges, we will achieve that goal. And also we want to achieve it with a minimal weight of the edges we remove. What we see in previous works is a paper by Nagarajan and Ravi in 2010, in which their approach was using an LP with solving the problem on trees. And with trees, they achieved a solution and approximation of log R, where R is the sum of all the requirements in the problem. And for general graphs, they embedded the graph into a tree and solved it on the tree. And when they embedded the graph, they lose another factor of log n, where n is the number of vertices in G. In the next paper they published with Gupta, they managed to improve the result for trees to log G, where G is the number of sets. And also they improved the way they embed the graph, a general graph to a tree, and that they improved to log K, where K is the number of all the vertices in the sets that we receive as input, instead of all the vertices in all of G. And also they show in this paper that they achieve log G as a lower bound for trees in this problem. They showed this with a reduction to set cover. In our work, we show a polynomial time randomized algorithm, and we achieve an approximation of X, which is the size of the biggest set, and then we have a factor of log R, where R is the same as before, the sum of all the requirements. And then N is the size of the graph, all the vertices in the graph. And then we have another factor of the square root of log N, and then log N. So we see that this is incomparable to the previous works, but it is better when X is small, specifically when it is smaller than the factor shown here in the bottom of the slide, where K, as we recall, is the number of all the vertices in the sets, and G is the number of the sets, and R the same, the sum of the requirements. And so that is when it is better. In our approach to the problem, we used a configuration LP. Then we rounded the solution the LP gave us with randomness similar to set cover, and then we solved the configuration with dual separation oracle. In the next slide, I will explain these methods. In this paper, as said before, we show a different approach to the problem from the previous works. So instead of trying to solve the problem for trees and using edges as variables in the LP, what we do is we try to solve the problem for general graphs, and we use the cuts as the variables. And if we look here at the LP, what we try and do is to minimize the delta and the lambda of the cuts, where delta is the weights of all the edges crossing the cut, and lambda is a variable indicating the probability a certain cut will be picked. And then we have constraints that are mainly on the sum of the lambda of the cuts. And what we notice here is that we have an exponential number of variables, as the number of cuts is exponential, and a polynomial number of constraints. In order to solve the LP, we would have liked it to be the other way around. So that is why we need to use the dual separation oracle, which we will see later on. Now let's look at the constraints we have here. The constraints here are used to make sure of two goals. One is that we pick enough cuts, and the second one is that they are not overlapping with each other. These goals are important to us because we need enough cuts to make enough connected components separate from the rest of the graph, and also to make sure that a cut doesn't separate a connected component that was already separated. We don't want them to cover the same vertices over and over again. So the first constraint is used to ensure the first goal, where each cut is that is useful. That is to say, it actually separates a connected component from the rest of the graph. So the sum of those useful cuts is at least the requirement, the sum of the lambdas. And the second constraint is for the overlapping problem. And so we make sure that all the cuts that the lambdas are, their sum is bound by 1 to make sure the overlapping won't interfere with our solution. So after we have a solution from the configuration LP, we want to round it, and we use a similar method to the randomized rounding in the set cover problem, except for a few differences. So what we do is we take the lambdas of the cuts, and if the lambda is big enough, then we will pick it anyway. In this case, we chose it to be bigger than 2/3. And if not, then we choose it with a probability of lambda. And so we repeat this process until all the requirements are satisfied. So the main difference between this method and the rounding in set cover is that after an iteration, what we do is we resolve the configuration LP, because this approach is a bit more complicated here than the one in set cover, and this makes the solution and the proof also a bit more complicated. Now here we can look at an example. Here we can see the graph we saw earlier, with a lot of different cuts, and we want to separate the green set, let's say, to 3 different components. And so let's see, for example, after a run of the algorithm, let's say, oops, it picked these 3 cuts. So E, D, and E plus D together. So it will look like this, and that is a valid solution. As we know, we wanted to separate it to 3 different connected components. What we want to see here is that we have 3 different cuts, but what happens is that they only break 2 different connected components from the rest of the set. And this is the problem I was addressing earlier when I was talking about the constraint on the cuts. And the main issue in our paper is lowering this bound on the number of pieces the set is broken into. And this is the reason we have the constraint I was talking about earlier, that that bounds the number of vertices the same cuts can cover. And so we see why this is important here in this example. As we recall in previous slides, we talked about the problem that we have with the LP, which is that we have an exponential number of variables and a polynomial number of constraints. Now, we would have liked it to be the other way around in order to solve the LP. So that is why we need the dual separation oracle. And this is what we are going to show here. So for the the dual separation oracle problem, we call the sparsest requirement cut problem. And it generalizes the sparsest cut with general demands. And we receive as input here a graph and a set of edges f that is a set that we removed from the graph. And we have also for each xi the y's that partition it in the graph G without f. Also, we have weights for the edges and weights for each set x, and also weights for each vertex. And what we want to achieve here is a cut S that minimizes the following ratio. And in the denominator, we have delta S and a sum of the vertices weights. And so the delta S here, as before, it states the weights of the edges crossing it, and the sum is self-explanatory. And in the denominator, we have a sum of something called cross SI times ZI. Now, cross SI dictates here so the y's we have for each x. So we want to count how many times S cuts those y's, and then we have ZI as the weights of the group of the set I. Also, so we see that if we have here each x at the size of 2, and the weights of the vertices as 0, then we capture the sparsest cut with general demands. As our problem generalizes the sparsest cut with general demands problem, we achieve only an approximation for the dual separation oracle, and the approximation is depicted here as x is, as shown before, the largest set we have, and k is the union of all the vertices of all the sets x. And so this is what we achieve here inside the O. We achieve it similarly to what was done in the work of Aurora Lee et al. In 2008 with the embedding of the sparsest cut with general demands. Also, we noticed that for the case that all the x's are of size 2, we achieve our result matches the same result as the best one for the sparsest cut with general demands. Thank you all for listening to my talk.